Thanks for the invitation, and it's always nice to actually have an audience that is different from what one is used to. So I want to start with just a definition of a matroid, and it's something that is around for quite a while, and it was sort of started by Whitney in the dark ages of the last millennium. But a matroid is just a finite set and that's finite set is called the ground set, together with some collection of subsets of that ground set. And these we want to call the bases of M. And then there is only one axiom in connection with that, with the bases, namely if I have two bases and they are distinct from each other and there is an element in B1 minus B2, then I can find an element of B2 minus B1, so that if I join this one element from B2 minus B1 to B1 and take out X, then I have another basis element. So what is clear from the start is that all bases have to have the same size, if this is supposed to be true. So this is coming out sort of, I try to view this, make this viewable graphically. And the alternate basis axiom says, well, I don't have to concentrate on what I want to throw out. I want to just concentrate on what I want to put in. But of course, that's the same thing. So one is used to the space exchange axiom from vector spaces. So if I have my black coordinate system and the green one, those are two bases for my 3 space, then I can exactly do that. If I have my heart set on throwing X out and putting Y in, I can always find such a Y in the other coordinate system. So that is just one of the axiom systems. And the interesting thing about matroid theory is that it can be defined in so many different ways. Basis is one of them. Then independent sets is quite naturally in connection with that. So any subset of a basis is an independent set. And for the dependent sets, minimal dependent sets, which we call cycles, is also quite clear. Dependent set is something that isn't independent. And spanning sets are the ones that contain a basis, and there are several others. And so this was really the achievement of Whitney in 1935, that he wrote this wonderful paper detailing all these approaches already. But the paper lay dormant for many, many years until Tutte came around and talked about combinatorial geometries. And everybody thinks that Whitney must have been the referee, because he said, well, there is this 1935 paper that essentially contains all your results. But if you call these things matroids, like Whitney did, then you can publish, because it's quite a different approach. So that is an interesting thing, that Tutte really got matroid theory starting. And just a few years after Tutte's text, Welch's text appeared, and it is really some comprehensive account of what happened in matroid theory since Whitney. And Welch really takes this from the graph theory approach. So his major driving examples are graphs. And Oxley has more the geometric and algebraic approach, and he has now it's a very successful textbook. Regke has a little bit of an applied approach from the engineering. And I think the most recent is the Spitzulis textbook, which is quite nice to read and more modern, and even extending these things to infinity, because all these previous texts were on finite ground sets. But now that we know what a matroid is, we want to just talk about a delta-matroid. That's something that was invented by Bouchet about 30 years ago. And he said, what happens to a matroid when you replace the exchange axiom, which contains the set theoretic difference, by just the symmetric or set theoretic minus, replace that by the symmetric difference. So take the union minus the intersection, and that's the symmetric difference. And so nothing much happens if x and y are sort of distinct, and we look at the symmetric difference, we get what we got before. But we can have now not the restriction that x and y are in the different sets, right? So this is the big difference, that now we get a set that satisfies this exchange axiom and got smaller because we are throwing both of x and y out. But it could also be the case that our set gets bigger because we are taking x and y both out of the second set, and we are putting them both into F1. And of course, in this way of writing it, x and y could also be identical, right? They are not forced to be different anymore by just this little definition. So there are several options. Either your set could stay the same size, it could increase by 1 or 2, or it could even decrease by 1 or 2. So our bases don't have the same size anymore. So what Bouchet called his sets were feasible sets, and that's why we talk about this collection F as the feasible sets. And there were many attempts in some sense, right? That's a lot of different terminology that sticks around, but Delta-matroids is the one that caught on and is used in recent publications. And these have actually quite nice applications for algorithms, because whenever you have a matroid, you actually have a fast algorithm to find a set of optimal bases, and it's just a greedy algorithm. So in some sense, the matroids are just the objects on which the greedy algorithm finds a basis. And Delta-matroid is actually an extension of the matroid idea. And these are called jump systems because you jump either by 1 or 2. And they also have applications in algorithmic approaches. So how are Delta-matroids and matroids related? Given a Delta-matroid, and the interesting thing is there are only feasible set axioms known for a Delta-matroid, and the variety sort of for how to define matroids disappears for the Delta-matroid. But there are two matroids which are inherited by or apparent in any Delta-matroid, namely the upper matroid. And I look at feasible sets with largest cardinality, and those feasible sets of largest cardinality are the bases of a matroid, which is called the upper matroid. And the ones with the lowest cardinality, they also have all the same size. They satisfy the basis axioms too, and they together form the lower matroid. And then you can just sort of study the relationships between the upper matroid and the lower matroid. And then you say, it's quite apparent that everything that is spanning in the upper matroid must be also spanning in the lower matroid, or then if F is spanning in the lower matroid, then it's also independent in the upper matroid. So one could think of, if I have two matroids, an upper matroid and a lower matroid, and I ensure that every basis of the upper matroid is spanning in the lower one, and every basis of the lower matroid is actually independent in the upper matroid. can I then construct a delta-matroid with those two matroids in mind? And you say, well, if certainly that construction cannot be unique if it exists, because I can write down some very simple examples and say they have the same upper and lower matroid. So I can write something very simple as the upper matroid consists of these two elements, just that one set. Then I throw in two sets of cardinality 1 and the empty set as my feasible sets. Then the upper matroid is AB and the lower matroid is the empty set. And apparently that's another delta-matroid, and they have the same upper and lower matroid, but they're not identical. So what we want to do is, given an upper matroid and a lower matroid, can we construct a delta-matroid which has the given matroids as the upper and lower matroid? And so one example that is, of course, dear to my heart is the rigidity matroid for a graph on n vertices and however many edges. And I want to say that I know the rigidity matroid, and the driving example for the definition of matroids was the connectivity matroid. And can I now construct a delta matroid going from one to the other? And I could say, well, I take a graph and my ground set is the edge set of the graph. And I look at the connectivity matroid and the rigidity matroid, then certainly the rigidity matroid has the higher rank. The connectivity matroid should be then the lower matroid. And then I can define my feasible sets by saying any minimally overbraced graph or any isostatic or any independent set of edges should be certainly spanning in the lower matroid. That's quite clear, because anything that is actually rigid in the upper matroid is definitely too connected. And so I don't have to say very much. And I can then show that if I say that under certain conditions, what my feasible sets are, right? So this is sort of the hard part for in between. Can we say what we mean by a feasible set that is consistent with the symmetric exchange axiom? So connectivity is not quite necessary, because I can construct a very simple example, say on 6 elements that where the upper matroid is just a simple cycle, right? So I say all the sets are bases which consist of 5 elements of them. And for the lower matroid, I could say, well, I take independent sets of size or bases of size 2, but they are either containing 2 numbers or 2 letters. Right? So that would be the disjoint union or the direct sum of U23 and U23, the uniform matroid of rank 2 on 3 elements. And it's quite easy to see that this is delta matroid. And you could interpret, say, the top one as the tetrahedron, so the rigidity matroid of the tetrahedron, which is a simple cycle, 2-dimensional rigidity matroid, I should say. But for a graph here that has just these 2 cycles, 1, 2, 3, and ABC, that is not possible as a graph, right? So it's not the matroid that I'm looking for. So what we are looking for is some condition. So if I want every cycle in the upper matroid to be sort of mapping down to something or coming from somewhere from the lower matroid, then we could say that every cycle in the upper matroid should be a union of cycles in the lower matroid, and we don't care about connectivity or spanning or something like that. So we can see by examples that the weaker condition is necessary, because if I look at my graphic matroid, then I could say that the graph on the left has rank 3, and the connectivity matroid, every spanning tree has 3 edges. And on the graph on the right, every spanning tree has only 1 edge. So the graph on the right should produce the lower matroid, and the graph on the left, the upper matroid. But every basis of the lower is actually independent in the upper, and every basis of the upper is spanning in the lower. So this could not possibly, the cycles are not a union of cycles in the lower matroid. And we know that there is no delta matroid that has these 2 connectivity matroids as upper and lower matroid. So then we can show very easily that the condition that every cycle in the upper matroid should be a union of cycles in the lower one is actually necessary. And then we can prove very simply that every basis of the upper one is actually spanning in the lower, and every basis in the lower matroid is independent in the upper matroid, and we can produce a delta matroid from this information. And so now we have necessary and sufficient conditions for realizing upper and lower matroid as the upper and lower matroid of a delta matroid, namely if and only if every cycle in the upper matroid is the union of cycles in the lower matroid. So then if you read Oxley's book, he has this wonderful theorem in there, a quotient of a matroid M. A matroid Q is a quotient of a matroid M. If there is a matroid N on the ground set of the 2 matroids, union some set X and some basis set, so that the intersection of E and X is actually empty. But what we get out of this is that one of the matroids is given, namely the big one, is actually N, where X is contracted, and the Q1 that we want to realize as a quotient is the contraction of N with respect to X. So here, this is the deletion of X from N. So, and he says that this is sort of a nice consequence of this definition, that Q is a quotient of M if and only if every cycle in M is the union of cycles in Q. So then we can reformulate that given 2 matroids, an upper and a lower matroid, then these are upper and lower matroids of a delta matroid if and only if the lower matroid is a quotient of the upper matroid. And so what is quite nice is to say X is not given, right? And there are lots of research problems that say, what is X? If I want to know what the quotient is, or that 2 matroids are related by this quotient relation, the construction of X is actually quite intriguing. And the nice thing about connectivity and rigidity matroid is that if I take my graph and I know it's rigidity matroid, then I know that coning is very nice construction in the rigidity world that if you actually adjoin to a rigid graph a new vertex and attach it to every vertex that you had before, you definitely get a rigid graph. And now if you take these new vertices, new edges that you have created to be your set X, then it is easy to show that the rigidity matroid is actually this coned graph with X deleted. And if you contract that X in a matroid sense, then you actually do get the connectivity matroid of the graph. So to show that, and then this would give me the entire information about the feasible sets in between. So this is actually some quite nice approach to understand the connection between, say, applications of the matroid and delta matroids, and to see the connection of the various matroids through the lens of the delta matroids. But what I want to sort of concentrate on is a little bit of the combinatorial maps and delta matroids approach. So when Tutte wrote his fundamental paper on maps, and it has the nice title, "What is a map?" He actually says that maps are usually presented as cellular dissections of topologically defined surfaces. So I need the topology first to say what a surface is, and then I can draw something on it, and then I can take the cellular approach. And so what we want to see that though, what are maps combinatorially? Can we define them in a purely combinatorial way without appealing to topology first? And so what his idea was, okay, look at a map, right? What is a map? So I have two vertices on that map. They are joined by an edge. And now I want to look at this edge and say, what am I looking at, right? So it's associated with 4 flags, and they are corresponding to the triangles in a barycentric subdivision. So if I look at the face and I put the barycenter in each face, then I want to connect that barycenter to the vertices and to the midpoint of an edge. So you see the edge divides 2 faces, and to each edge there are 4 of those little triangles that Tutte calls flags associated with that edge. And then the nice thing is that the map can uniquely be described in terms of 3 perfect matchings, namely the flags are different. So if I look at flags that actually share 2 things, like for example, a vertex and an edge, then if I flip from one face to the other, then I have a matching between the 2 faces that the 2 flags that share part of an edge. If I look at 2 flags that share a vertex and the vertex in the center of this edge, then I don't change face. And then how do I change vertex? By that's the 3rd perfect matching. So I've drawn here the barycentric subdivision, and now I want to sort of look at my 3 perfect matchings, right? So if I look at, say, one of these triangles from the barycentric subdivision, it's related to a triangle over here. By flipping around, they keep the same vertex. And I draw this edge in black. And if I look at the 2 triangles here that keep the edge, but flip, keep the edge and the vertex. So they are connected by green. And then if I flip to the bottom, then I draw in a red edge. And so I've now drawn in a graph that realizes these 3 perfect matchings. So, and Tutte proves that actually this map graph uniquely encodes the mapping. So the map can be uniquely described in terms of the 3 perfect matchings. And now I can just look at the map graph and want to recover, of course, faces, Euler characteristic, orientability, and all of that. And what are his axioms? Right? So I want to start out with now a graph that has edges of 3 kinds, the red, green, and the black edges. And each color class should be a perfect matching. And red and green, they came from the edges. They should just be forming a union of 4 cycles. And overall, the map graph should be connected. And now we want to sort of use this object to study maps. And Tutte's big success was that just by looking at deletion and contraction of edges, that he could recover the classification of maps into unions of spheres, handles, or what is it, projective planes, and tori. So now what we want to say, one of the important things when you're studying that map graph from these 3 simple axioms is that there is no restriction. It's actually not necessarily a simple graph, but it can have parallel edges and all sorts of things, right? But one particular nice thing is that gamma contains 2 regular subgraphs which use all the black edges and which we call fully black 2 regular subgraphs. And for example, red and blue are some of these fully regular 2 colored subgraphs, and green and blue, green and black. And these correspond necessarily to the vertices and to the faces of the original map. So, but what is also nice is that this map graph is always Hamiltonian, and it contains certainly several Hamiltonian graphs, and they all must contain all the black edges, because after all, it's a 3 regular graph. And so that's the interesting part. And this we can use to actually get a Delta-matroid from the map graph. And we just define, or we just look at all the fully black Hamilton cycles. And we specify one of the color classes and say, then our collection F consists of all the subsets corresponding to pairs of green edges in a fully black Hamilton cycle. And we can prove that this is actually a Delta-matroid. So this is the idea, right? We have to just see what the exchange axiom tells us. And what can the situation be that we want to look at, you know, a pair of edges that I can throw out. And I say that, well, if I disconnect my Hamilton cycle by the removal of these 2 green edges, because it contains some green edge, then I can reconnect another way. and by just twisting the two edges. And so we can prove the exchange axiom quite directly, right? And if I want to look at the fact, if I get more than one component, then I can fix my connectivity yet again by adding or removing pairs of green edges. So this is nice thing. And now we want to see in that delta matroid, what are actually the upper and the lower matroid. And now we can see what we have for graph, right? We know that the edges are encoded by the red-green quadrilaterals, and the vertices are actually green and black, two connected subgraphs or two regular subgraphs, and the faces are the red and black subgraphs. And now we can see that what is the upper matroid and the lower matroid. The lower matroid of this delta matroid that I got from just looking at green in a fully black Hamilton cycle is nothing but the cycle matroid of the graph. And the upper matroid is the co-cycle matroid of the geometric dual. So I want to give you not necessarily the proof of this, but it's just sort of really straightforward, and what you get out of it, that the upper and lower matroid differ in rank by 2 minus the Euler characteristic of the surface. And what you also get, if gamma is bipartite, then all the feasible sets have the same parity, which comes out quite nicely from just the map graph. And so if you have a non-bipartite graph, you will get in your delta matroid feasible sets that don't have the same parity. So in the bipartite case, or in the orientable case of a map, the delta matroid must have all sets of the same parity. And if the map is not orientable, then the delta matroid has sets of different parity. So I want to just run you through some detailed examples so that you know what we are talking about. So here I have just one map graph that certainly satisfies top 3 conditions. If you look at red and green, we get quadrilaterals, and the black edges form a perfect matching also, and the whole thing is definitely connected. Now what I want to see is what's my upper matroid and my lower matroid. So I go for green to be the that where I want a fully black Hamilton cycle that contains exactly these quadrilaterals that have green edges. So I walk around green for all of them that I have specified here. So let's check, for example, if 1, 3, 4 is a feasible set in this delta matroid. So let's start walking at 1 at this upper corner, and then we go black. And now 5 is not in my feasible set. So what I should do is walk around the red edge, because the green edge is not in my fully black Hamilton cycle. So I walk around the black edge first. 6 is also not contained in my feasible set, so I walk on the red edge and I go my black edge. 2 is also not in my thing, so I must walk around red again. And now 1 is however contained, so I use the green edge and I go to black, right? And 2 was not there. I have to follow the red edge. then I follow the green edge, green, and I follow my Hamilton cycle is sketched out. I get back to 1, and I have traveled through my Hamilton cycle using green edges from 1, 2, from 1, 3, and 4, and using the red edges on 5, 6, and 2, which are not in my feasible set. So you list all of the feasible sets by this marching through. But a nice thing is you get the graph, of course, as described before. A graph, the vertices are, say, let's say 3 and 4, red, black is a vertex of my map, and that corresponds to this vertex down here. Then 1 and 2 are sort of the quadrilaterals correspond to the edges of the graph, right? And those are parallel edges because I have this connection here between this face, which contains only the edges 1 and 2. And 5 and 6 are also a parallel edge. And then I have drawn my graph as actually 4 vertices. Those are the 4 red-black cycles and 6 edges. And by the same token, I can do this same thing for the geometric dual. And now I can look at my feasible sets. And what you should recognize here, all the feasible sets are actually of the same cardinality. So how is this a delta-matroid? Well, it has a delta-matroid by the simple fact that the upper and lower matroid are identical. Right? So this is actually quite nice. So what does this tell us actually about the graph? This is a map on the sphere. Right? So if you take the geometric dual of the map on the sphere, then you get another map on the sphere. And this is sort of recognized right here. So somebody gave me, this is a Delta-matroid, and here are the feasible sets. But the amazing part is, can you recover the graph? Do you actually know something? Well, you know that, you know definitely it's coming, if it's coming from a graph, that it's coming from a planar graph. So it's a question, if you don't have the information of your map, how can you recover the graph? From this information, this might not be enough. But let's make a little change in our map graph. And all I have done here, I don't have to check if this is a map graph, right? I've only changed actually one of the vertices. So it's still a vertex because it's a red-black cycle that connects, or that is in attachment to these to the edges 1, 2, and 3. So I have not changed the graph at all, right? But I have changed its geometric dual. And if I now play my feasible set game, then I do get elements of larger size. I get to 1, 2, 3, 4, 5, and 1, 2, 3, 4, 6. And that's sort of interesting. So the dual graph now only has 2 vertices and this shape, right? So this is the geometric dual. And what do I know? All the feasible sets have the same size, and the upper and lower matroid differ in rank by just 2. And now I can say, where am I? I'm actually on the torus. Right, so just from this Delta-matroid information, you see that you have an orientable map, and it's a map on the torus. Well, now we can take this one more step. So I can make with my edges 1, 2, and 3, yet another graph by connecting or making this matching of the black edges between those vertices this way, right? And I play my Delta-matroid game, and I get yet another feasible set, which is just 1, 2, 3, and 4. But now this has an even size, right? My graph and my dual graph actually are the same as before, but I get this feasible set of size 4. So I know my map is not on an orientable surface. So again, this distinguishing feature came not from the graph that was embedded or the graph of the geometric dual. The Delta-matroid information gives me the fact that these were both embedded. Not only are they geometric duals of each other, but they were embedded on a non-orientable surface. So it's clear from these examples that in general, you cannot recover the map from the Delta-matroid information. But in some cases, you actually can recover the map, namely if your graph and the dual graph are connected enough. So what you can say, and you can sort of realize the connectivity in terms of the upper and lower matroid, because a graph is, if the matroid is 2 connected, then you know that the corresponding graph is 3 connected, and that the matroid of the corresponding graph uniquely determines the graph. So that's the nice thing about matroid theory, that you can have, say, the bases listed, but just as sets, and you can recover the connectivity or the adjacency uniquely, provided you have enough cycles, provided you have a highly connected graph. And what this actually amounts to, and the co-cycle matroid is sometimes harder to understand, but the graphic matroid is actually of a planar graph, is characterized by the fact that the facial cycles generate the cycle space. And now you can say a 3-connected graph in general is characterized by the fact that the vertex co-cycles generate the co-cycle space. So if you put those 2 things together, then you can say if both G and G star are 3 connected, then the map is uniquely recoverable from the Delta-matroid information. So I want to just run you through one example of this. So here I have pentagon, right? And so complete graph on 5 vertices. And so I have 10 vertices, 10 edges. And I look at the geometric dual of that graph embedded on the torus. And now I have sort of translated this picture. Of course, the picture doesn't tell you anything about the map or the torus. But if you actually look at the vertex coloring of the geometric dual, those colors should actually correspond to the little squares here of the same color. And so this is sort of the map as depicted on the flat torus. And now you can sort of check this. So this yellow vertex is probably the easiest one to see, has edges sticking out of it, which are called capital B, capital D, little d. And if you look at one of these yellow faces, it's surrounded by little d, capital B, and capital D. And that's the idea. And if you take the geometric dual, you can sort of see that it's actually a nice embedding of K5 on the torus, namely one that's self-dual on the torus. And in some sense, it's sort of fun, right? So that if you have your Delta-matroid information, and the Delta-matroid information tells you that the lower matroid is the graph of K4 and K5, and the upper matroid is the co-cycle matroid of K5. And that's what we are actually saying. So that the upper and lower matroid are perfectly isomorphic, but since we are going for the co-cycle matroid of 1, then we are looking at the cycle matroid as the lower matroid and the co-cycle matroid of K5 as the upper matroid. And if I know the Delta-matroid information, I can recover my map. And I think that's quite spectacular success for looking at this completely combinatorially. Well, I want to now use these ideas to get a little bit further. So this is sort of what we are thinking about at the moment. So if we look at the rigidity matroid of for graphs on surfaces, so far all the methods have been using some sort of machinery coming from actual embeddings and looking at sort of really constraint systems in differential equations and all of this, right? So what would be nice here is to get to a theory where you represent the surface by a polygon and identifying boundary conditions, and then represent your edge set by straight line segments that might cross or might not cross. And then, well, what do I do if they cross? So in the plane, we have something very nice that if I draw my edges, say for a tetrahedron, of course, if I want to do it in the planar fashion, and I want to study the rigidity matrix of a tetrahedron, I don't really care how I have embedded it. But if I know it's embeddable in the plane, why don't I do that? But do I have to really, in order to study the rigidity matrix, know exactly how to draw it? And the nice thing about drawing it badly, from the rigidity point of view, I can say this is a cycle in my two-dimensional generic rigidity matroid. And if I insert a vertex in my drawing that wasn't so planar, that is still a cycle in the generic rigidity matroid. So if my graph is embedded on a surface and edges cross, then the vertices of degree 4 don't really disturb the count. And so rigidity in the plane is characterized by an edge count, right? So there should be enough edges to achieve rigidity, and there should not be any more edges to achieve rigidity in a basis. And the count is twice the number of vertices minus 3. The minus 3 comes from the isometries of the plane. And you see that vertices of degree 4 don't make a difference to that count. So a cycle is characterized by 2 times the number of vertices minus 2 edges and no substructure overbraced. And of course, doesn't make a difference if I add a vertex of degree 4, then I have subdivided coincidentally also 2 edges that are that were crossing beforehand. And that's a sort of nice exercise in rigidity theory. It's called X replacement. So if 2 edges cross, you want to put a vertex right there, and you don't disturb the rigidity properties nor your cycle structure or basis structure of your matroid. So I can do this various different ways, and I can generate many planar cycles that way. And the nice thing is planar cycles dualize into cycles, right? And we actually know this from the Delta-matroid information, if you like, right? So now what about the rigidity matroid itself? The rigidity matroid is just what's called a Dilworth truncation of 2 cycle matroids of G. So the cycle matroids are there, right? So this truncation comes just from the fact that if I have a basis in my graph, basis has rank number of vertices -1. And if I put 2 of them together, I get 2n - 2. But for the rigidity matroid, I want 2n - 3. So 2 of these trees should give me something that is dependent, but only by 1. So that's why I call this a truncation. So that holds for the 2-dimensional generic rigidity matroid. So now what is the fact actually? If my graph is planar, then that rigidity matroid is a map on the sphere. And the upper and the lower matroid are identical. So I can say that this rigidity matroid of my graph on the plane, by putting these extra vertices where edges cross, is actually just a truncation of the upper and lower matroid put together. So that's what I want to use to actually study graphs on surfaces. And just sort of a side consideration, if I ask myself, well, I specify this polygon, I want to actually study rigidity on the torus. And now I place my sort of vertices sort of randomly, and I want to use sort of the straight line distance to closest vertices as my edges, then what's the probability that I actually do get something connected on the torus, or a real map? And that probability is actually quite sufficient that you say asymptotically, almost surely, this approach yields a map. So I don't want something that isn't connected in my map sense. And now I want to suggest to study the rigidity matroid of a map on the surface as a truncation of the union of the upper and lower matroids of this delta matroid.
We're just about out of time. I'll let you just give us one more minute to wrap up.
Right. So handle slides is something that is known in the world of ribbon graphs, and they are intimately connected to study surfaces. So we want to just look at a normal form in terms of these handle slides, because handle slides in the original sense were only defined for really adjacent sets of things. But in the Delta-matroid world, you can just do it ordinarily, except it's only really defined for binary matroids or binary Delta-matroids, which I didn't get into. But this is something that we are working on right now. And I just leave you with the bibliography, and sorry for going over time and sorry for being late. Thank you.
Let's go ahead and thank our speaker.